ball-shaped on these stalks. Nymphs, 5 instars, and they're fairly sedentary, but they can move if they are challenged or tipped. And they do secrete a toxin. That's really the damaging part of the potato psyllid, is this toxin that causes what we call psyllid yellows. And that's separate from zebra chip and that whole phenomenon. So there are really 2 types of damage, vectoring this toxin that's inherent in the psyllid, and then the bacterium that causes the zebra chip. So then we go to the adult stage, which is not actually damaging to potatoes. And so yeah, we did not really get much notice of the potato psyllid until recently, and followed by the zebra chip outbreak we had in 2011. And so, of course, we're located, I'm here in Western Oregon, but most of our potatoes are along here in Eastern Washington, Oregon, and then parts of Idaho. It's a major potato production region, as you know. So the thing about potato psyllid is that there are 3 or more haplotypes in the US. And at the time that this paper came out, there were 3 identified haplotypes. Newly discovered, we have the northwestern haplotype that overwinters successfully here. And then older, much more knowledge had been gathered about especially the central haplotype that overwinters in the southern US and migrates to the north, as shown here. And so yeah, there's a common long distance migration that happens in the Midwest, and many of these make it all the way to the Northwest. So there's really a mixture of haplotypes that are found in Washington, Oregon, and an even greater mixture are found in Idaho. So the Western haplotype is on the West Coast in the South, and they migrate north each season. And so there's going to be a difference in phenology models if you were to model the central or the Western or the Northwestern haplotypes. I tried to combine them all into a common model, which may or may not be successful. I haven't gotten feedback that from people in Texas about my models, so I don't know how well it performs there. It seems to work well in the Pacific Northwest, and our primary users are going to be here in the Northwest. If you take a look at the latitude, of course, you all are probably aware, if you flip New Zealand and line it up with the Western US, it lines up pretty well with Oregon, latitude-wise and climate-wise as well. So we have a lot of climates in common. Maybe that's why potatoes, I'm not surprised you have a big potato industry, because you have, it sounds like a good climate to grow them. Let's see, what else? So in New Zealand, I guess you first got the potato psyllid in 2006, and now it's been spread throughout the country. I think that's about it for this slide. Of course, adults are known to flee the field when the days get short and the weather gets cold in the fall. And so the psyllids are well known to overwinter, kind of like aphids. They will seek out shelter in trees, in the bark, and especially in coniferous trees. But we're finding for this northwestern haplotype that seems to be the predominant one in Oregon and Washington, that it actually continues to develop, albeit at a very slow rate, on wild hosts, such as Bittersweet Nightshade seems to be the #1 host here in the Northwest. This is an invasive weed, and it's been found to be pretty common. And so it is a source of this pest and of zebra chip. So, and it's also cold tolerant, so it's a really good host for potato psyllid. And so I think you have the equivalent hosts in New Zealand, and I think you have the same things going on, but you can bring that up during the questions, I guess. but essentially it can oviposit early in the spring. March here in the Northwest, and that would probably mean September or early October in New Zealand. And since we have similar mild winter climates, I don't think the long distance migration is really necessary, but we might have a very cold winter that might wipe out these local populations to some degree or really knock them down. So it might be this component of long distance migration could be an important one as well in the Northwest and probably in your region as well. They've used the Maxent method to try and determine the climate suitability for both the potato psyllid and zebra chip, the bacterium. And it's pretty much anywhere you can grow potatoes, you're going to have these two pests. So throughout New Zealand, throughout most of the US, the darker red is the most suitable and the orange is less suitable. So I don't know how you could grow this psyllid in these parts of Australia or, you know, in the extreme north of North America, but that's the result that this study came up with. So take it with a grain of salt, because I think it needs to be verified. So a lot of my modeling came out of this conversation I had with Andy Jensen. He was a fellow grad student when I was at Oregon State as an entomology graduate student. And he rose to become the research director for the Tri-State Potato Commission. And he's also an expert on potato psyllid. And he goes out on his camping trips, foraging trips. He's looking for potato psyllid everywhere he goes. And so his notes lend a lot of credibility to this whole hypothesis that they do succeed in overwintering on nightshade. He believes there's one full generation in the spring on this bittersweet nightshade and other wild hosts. And then there are 3 or more generations on potato. And then when they leave potato in the fall, they go back to the nightshade and they'll develop 1 or 2 more generations. So that adds up to 5 or 6 generations per year. I think it might be, the average might be a little less than that, like 4 to 5 in our region. But I haven't really, actually I did an analysis and the average I got was 5. So yeah, he's within the range of what the data say or have told me. So yeah, it has this annual migration pattern, and it can be both short range and longer range, especially for those haplotypes that live in the south in the winter. It's been known to seek higher altitude, so it goes up mountains and hills. Especially it gets triggered when the weather gets hot. And so I'm wondering if we could derive a threshold temperature for migration to avoid these extremes in heat. And I would guess it would be somewhere around 32 to 35, which would be 95 Fahrenheit. So it also has no reproductive diapause. So if the temperatures become more favorable in the winter, as with climate change, it could be developing and increasing in numbers to some degree in the off season on these wild hosts. And so it's responding to the temperature and to the availability of food in its host plant as the primary limit in the off season. So going now to how I did the modeling. Well, I've already explained that trans work, which is what most people are relying on for building models. In the same graph, he shows for the same data, he's leaving out the 8-degree and the 10-degree points for some reason. And I think he explained the reason was that at these low temperatures, the host was degrading, and they were constantly having to move the nymphs onto fresh host material, and this was causing excessive mortality, all of the handling. And so they were pretty uncertain about these 2 points, but they left them out. See, in the egg stage, here's the 10-degree point. They left out the 8 and the 10-degree point for the nymphs, as well as for the egg to adult fitting of the model. So you can fit the model for any life stage and for combined life stages, as he did here. And then I left out the middle graphs, but just showing egg to adult for this lactin this is the graph I showed earlier. It is linear for the cooler temperatures, but it's nonlinear to fit the high temperatures that are suboptimal because we're getting increased mortality. As you all know, we get to sort of an optimum at the fastest rate. But even then, often the mortality is slightly high. And then we get even higher mortality rates as we get higher and higher temperatures. So of course, that's only one point to fit this whole part of the graph, but the rest of this curve looks really good. And he did include the 8 and the 10-degree results. And so when you fit that to the x-intercept, you get 3.5 degrees Celsius. So you really cannot say that Tran's results that he reported of 7.1 is the threshold. He got this range, and it just depends on which curve he used and which points he included. So, you know, I tried to digest that back in 2017, and I always redo the analysis anyways, because I don't, you know, I'm combining different studies. And so when I looked at his data, I was looking at Lewis at the same time. I shouldn't say too much about Lewis's results because he was looking in Texas, in southern Texas, so it's very hot there, and that's the central haplotype. And so Lewis found a lower threshold of 6.5, so that's well within the range of what you would expect. For a warmer adapted species, it would have a higher threshold. But the way I did it, I fit the same data that are reported in the literature, so Lewis and Tran, I fit them without forcing an x-intercept. And then I do the same thing where I add a point to force the x-intercept through my chosen threshold. And I typically pick an odd or an extra decimal point with Celsius so that I can get an even number with Fahrenheit. So that's kind of the rationale for 4.4. It seemed to be within the right range and yet come up with an even number for Fahrenheit. And you know, you always track the R-square and see what you're doing to that. And of course, with Lewis, I lowered the R-square from 0.996 to 0.969, which is still very good. It's excellent. And with Tran, of course, leaving in these 2 points, we get a T low. I think that's 3.5, the same that Tran et al. themselves got using the lactin model, only here it's just a linear model, simpler. And then I could easily force that to be a little bit higher. Instead of 3.5, it's now 4.4. And so the R-square actually improved a little bit from 0.975 to 0.977. So that's pretty much how I did the determination of the lower temperature threshold. And I've documented all of my doings, consolidating 12 different sources in this PDF file that's basically printing out of a spreadsheet. And it's a 9-page spreadsheet. It's tedious. It took me about 3 months to do this analysis. It took a long time. And it includes unpublished sources like the interview with Andy Jensen, and also the data from Hermiston that Sylvia Rondon and collaborators collected from the field. And so basically their results showed that there were nymphs and adults on these wild hosts all year long. So January, February, middle of winter, they were finding adults and nymphs. So it makes sense that the first I derived that the first oviposition by these overwintering females happens as early as 81 degree days after January 1st, which would be, I guess, July 1st would be your starting date for you all. And so it goes from there. Basically, that kind of initializes the model in the spring, and it's on this wild host. So that's something that probably would not make sense in the Midwestern US, where we have this continental climate where it's much colder in the winter. And so they're totally dependent on long distance migration. And so that would set up a different model. So keep that in mind, that this model probably really should only be used in the Pacific Northwest and in regions with a similar climate. Perhaps your region fits that. So if you take the overall results for different degree day requirements that were all fitted using a lower threshold that I settled on of 4.4 Celsius, all of the studies, we determined the degree days for each life stage. And then I did kind of a weighted average and kind of a little bit of a rounding exercise. So 504.9 just became 500 for the sum of egg and nymph degree days. And it's, of course, that's well within the range. We get a pretty wide range of results here. And Mustafa in Washington only had a humidity of 40%. So that may explain why these values are outliers, and they were much higher, because maybe these eggs and nymphs were being stressed because of the fairly low humidity, versus Tran et al. They used 55% humidity in their studies. So that study seems to be a lot closer to what we ended up with our final values. So yeah, and I cut out the center because there's just too much data to go through. But that's kind of how I do the process of modeling. I try to get a concordance of all the inputs and come up with either an average or a weighted average, or I discount studies because they don't pertain to what our needs are. So I guess my couple last thoughts here would be that as climate change is leading to milder winter climates, this northwestern haplotype is likely to increase in its population. It'll be more successful, and probably will have higher populations at the beginning of the season. And so that may cause earlier and greater impacts on the crops. These wild early spring hosts, I think, should be targeted for management if they're not already doing that. And so, you know, it's really rare to find off-season sampling of a pest. It's like everybody gives up, and it's too difficult. The numbers to sample are so rare that it's hardly worth our effort. But in this case, it really paid off in understanding adults and nymphs can survive in Eastern Oregon on this bittersweet nightshade. So that really defines how the model should be built. So of course, in the Pacific Northwest, they're adding different techniques to determine whether zebra chip is in fact part of the problem, because zebra chip often comes later in the season. The potato psyllid isn't always infected with it. And so they need to add that to know what the risk levels really are, because zebra chip, I have a slide that I took out because I knew I would probably run over because you only gave me 30 minutes. So I think that's about it. I'd be happy to answer questions. These are most of the references I used today. Thanks to